Hello everyone. Today we are going to see Operating System Unit 3 Session 8, and in previous session we have seen the various algorithms on the critical section and how to solve the critical section problems algorithms we have seen. In today's session we will see a new topic called semaphores. So this semaphore is a solution to n processes, means a number of processes those who are sharing the same variable. So what are the solutions till now we have seen? It was only for two process solution. So whenever we want to synchronize two processes, those who are sharing the same variable, that time the previous algorithms which we have seen, two process solution or the Peterson solution, those algorithms can be used. But when multiple processes, number of processes are sharing the same variable, then those algorithms does not work. So for such problem, in such cases you need to synchronize the processes so that the processes should not get stuck and multiple processes can share the share variable and the flow must be proper. So for this we are going to use semaphores concept. So to synchronize the processes, we have the critical section, and there are three conditions for critical section: mutual exclusion, progress and bounded waiting, and also deadlock. So these have to be implemented in that algorithm using these semaphores. So mutual exclusion, when one process is there in the critical section, no other process is allowed to enter into the critical section. And progress is that the processes those who are interested in entering in the critical section, only those processes can be allowed to enter into the critical section. And bounded waiting, should not be allowed the processes to wait in the loops for more number of rounds. Then deadlock, when the processes are accessing the same variable, then they should not go into the deadlock, means they should not go in a hanging mode. So these all must be synchronized properly using these semaphores. Semaphore is a solution for n process. Semaphore solves critical section problem. It can be used to decide order of execution among the processes. So the sum of the processes are dependent on each other. So we can also change the order of the processes, which process we want to execute first, second and third. So this can be also done using the semaphores. We can change the order of execution of the processes. Resource management. Semaphores are also used in managing the resources. Now suppose there is only 5 printers. Then only 5 processes are allowed to use the printers, and other processes have to wait in the queue. So such management is also done by the semaphores. So semaphore is actually a synchronization tool. It is a process synchronization tool, and it is nothing but it is one integer variable. Semaphore, yes, it is one integer variable, and it can be initialized and accessed on only 2 operations, which are those: wait and signal. So this semaphore is actually an integer variable which will operate on only 2 operations: wait and signal. So here wait operation is like a locking and a signal is like a unlocking. So we have seen in the previous session that processes before entering into the critical section, they occupy the lock and they enter into the critical section and they lock it, so that the other processes should not interrupt them. And then after finishing the critical section, they unlock it, and so that the other processes, those who are waiting in the queue, can access the critical section. Same way here, wait operation is used for locking it and signal operations are used for unlocking it. And this variable yes is always initialized to 1. Yes is equal to 1. So whenever you see yes is equal to 1, means we should understand that there are no processes inside the critical section. So whenever the semaphore value yes is equal to 1, we need to understand that there is no processes inside the critical section. And this is the steps inside that waiting operation. See, the value of semaphore is decremented here. And in a signal operation, the value of yes is incremented. So this was the earlier, see, at the earlier algorithm we have seen in the entry section, we were acquiring the lock and we were locking it before entering into the critical section. Same way here, in the entry section, wait operation is used for locking and then the processes enter into the critical section, and after finishing they unlock it by executing signal operation, and remainder section, whichever the remaining part is there, they execute it. So here in the entry section we are using wait operation, and in the exit section we are using signal operation. In a wait operation, yes value will be decremented and in a signal the yes value will be incremented. See, definition: the wait operation decrements the value of its argument yes if it is positive. Always the wait value, always the yes value is initialized to 1 in a wait operation. So obviously it is going to be positive. If yes is negative or 0, then no operation is performed. It gets stuck into the loop. The signal operation increments the value of its argument yes. So signal operation we used for unlocking it. So it is going to increment the value of yes. From 0 it will make 1 by incrementing. So critical section of AND processes. So this is the algorithm for that. For shared data. So semaphore, this variable is used. See, instead of yes we have used here mutex. So any variable name can we use. It's not that only yes variable we have to use. Any variable name we can use here. This is mutex, means mutual exclusion, and see it is initialized to 1. So always the wait operation variable must be initialized to 1 only. So the processes, those who want to enter into the critical section, they go into the loop and they execute wait operation. So when they come to the wait operation, we have the loop there. So in a wait operation you have seen we have loops. So the mutex variable, that is yes variable, is initialized to 1 now. So it enters into the, whenever it executes the wait operation, it enters into the loop now. Now here yes value is 1. Now 1 is less than equal to 0. See, condition is false here. Condition is not true. 1 is not less than equal to 0. 1 is not less than equal to 0. So condition is false. Then when the condition is false, it is going to make yes value decrement. So after decrementing, yes value is going to become 0. That means it has locked now. After locking, it is going to enter into the critical section. Then after finishing the critical section, you can see here it is going to come out. After finishing the critical section, it is going to execute now signal. In the signal, which code we have? Yes is equal to yes plus 1. So what was the yes value? You can see here. The yes value was 0 here. Now after incrementing, it is going to become 1. 0 plus 1. After incrementing, it is going to become 1. That means unlock. So whenever the mutex yes value is 1, it is unlocked, so that other processes, those who are in a queue, they can enter into the critical section. So it is going to make, at the beginning, the yes value will be 1. And when it goes into the wait operation, it makes yes value is equal to 0. And after finishing critical section, it makes again yes value equal to 1. So this is lock. Whenever the yes value is 0, it is lock, and whenever the yes value is 1, it is unlock. Now check for mutual exclusion. Now let us check for mutual exclusion. Let us go out for this. Okay, now the process P1 enters into the critical section. So first it executes wait operation, and always the yes value is initialized to 1. Okay, so 1 is less than equal to 0. Condition is false. So condition is false. Then it decrements the value of S. It makes now S value 0. So whenever the condition is true, we need to understand that there is already a process in the critical section. So whenever the condition is true, that process gets stuck into the loop. Now here the condition is false. So it has come out of that loop, and we also have a semicolon. Semicolon means it is one trap where the processes are going to get stuck when the condition is true. Now here S value will be decremented because condition is false. Now the process enters into the critical section and the S value is 0, so no any other process is going to interrupt there. So now suppose now other process comes, already P1 is there in the critical section, already P1 is executing in the critical section. Now suppose P1 interrupts in between and P2 wants to enter in the critical section. So P2 enters in the critical section. Now when it enters in the loop, see now the S value is 0 here. S value is 0 now. It checks for the condition. Now the S is less than equal to 0. See, condition is true now here. Condition is true. So P2 gets stuck into the loop now. P2 gets stuck into the loop. And whenever any processes are stuck into the loop, all the time it keeps on sensing the loop. It keeps on repeating and sensing the loop until the S value changes. It keeps on sensing it. So now P2 is stuck here and P1 is already in the critical section executing. Now P1, when it finishes the critical section, it executes signal operation. And when it executes signal operation, it increments the value of S. From 0, it becomes now 1. So after incrementing, S value becomes 1. So immediately when the S value changes to 1, that P1 comes out of the loop, condition becomes false, and it decrements the value of S again to 0. So that now P2 enters into the critical section and now P2 is in the critical section. So like this way the mutual condition is checked here, it is allowed. And progress condition will be also checked here because the processes, those who are interested, only those processes tries to enter into the critical section. Okay. So here chance are not given that P2 only has to enter, P3 only has to enter. So whoever wants to execute, though execute this wait operation and signal operation. So whichever process wants to enter into the critical section, they execute wait operation and signal operation. If there is already process in the critical section, then it will not allow to enter it, because if the S value is 0, we need to think that already there is a process in the critical section. If S value is 1, then we need to understand that there is no process in the critical section. So progress also have made bounded wait. Yes. Now we have seen here the processes waits into the loop and they keep on sensing until the S value changes. So immediately when the S value changes, that process is allowed to enter into the critical section, and that is the bounded wait. So at least one round they will be waiting there. So such processes should be not allowed to wait for a longer time. Types of semaphores. So binary semaphore is one type. So this binary semaphore is a mutual exclusion, whichever the example we have seen just now, that we call binary semaphore, and its range is only between 0 and 1, and it is also known as mutex locks, as they are locks that provide mutual exclusion. So binary semaphore is especially used for the mutual exclusion only. When one process is in the critical section, it will not allow the other process to enter in the critical section. So this solution, this binary semaphores, is for n processes, share a semaphore mutex initialized to 1. So when the semaphore value is 0, it is locked. When the semaphore value is 1, it is unlocked. The wait operation only works when the semaphore is 1, and the signal operation succeeds when semaphore is 0. So this binary semaphore is going to operate on wait operation and signal operation, and that is between 0 and 1 only for locking and unlocking. Next type we have counting semaphores. So this can be used to control access to a given resources. consisting of a finite number of instances. So this counting semaphore is used when you are managing the resources. Now suppose there is 5 printers, then only 5 processes you can allow to enter into the critical section. So till now we have seen that only one process can enter into the critical section. But in this resource management, if there are 5 printers, we can allow the 5 processes to enter into the critical section, not more than that. So 5 processes will execute simultaneously in the critical section. So this is how the resource management is done using the semaphores, and is initialized to the number of resources available. So the number of resources are available 5, 6, whichever it is, that much number of semaphore value variable must be initialized. Ordering of process execution. Now we can also change the order of process execution. As we know that the processes are dependent on each other. See, one process can be dependent on each other. So in such case, we can change the order of execution of the processes. So in a multi-programming operating system, there can be number of processes. Any process can be executed at any time. So depends on scheduling algorithms, which process is to be executed first and next processes. So there are some processes which are dependent on each other, must be executed after specific processes. So in this case we can use semaphores. See now, suppose take the program. Okay, now there is a program to accept a radius, and based on the radius it is going to calculate area of circumference, and it is going to calculate area of circle and area of circumference based on accepting the radius. So see, now see, first process is for calculating area, and second process is for accepting radius. It is going to accept radius, and third process is for calculating circumference. See, now first process is of calculating area, second process of accepting radius, and then third process is of circumference. But here process 1 is dependent on process 2. Now see, when you accept the radius, then only you can able to calculate the area and circumference. So process 1 is dependent on process 2, as well as process 3 is also dependent on process 2. So we are going to change the order now here. So the number of processes which have come for execution is in this order. The processes have come for execution in this order: process 1, process 2 and process 3. Now we want to change the execution of order. Now we want to make process 2 execute first, then process P1 should be executed next, and then process 3. Now we want to change the order. So for this we can take 2 semaphore values, S1 and S2, and both are initialized to 0 only. Now see here, when the process is, now see in this case what happens, even you give the chance for process P1 and process P3, they are not going to execute. The chance will be given back to process 2 only again. Because see, what is the semaphore S1 value is 0. So when the processes comes to waiting operation, see, it is 0 means what? It is not going to allow the processes to enter into the critical section. So the process which I entering here is going to stuck here. Process P1, if you give the chance for process P1 process is going to stuck here. So automatically the chance will be given to the process P2. Now we are not going to include here wait operation. So directly we are going to give the chance for process P2. P2 is going to execute the critical section. Now when the P2 finishes the critical section, it is going to give chance to the process P1. See, because we are included here S1, and S1 is used for process P1. You can see here. So semaphore 1 is used for process P1, and semaphore 2 is used for process P3. So whenever you say S1, that means process P1 chance is given. So here signal, when it executes signal operation, it makes the S value to 1. So whenever the S value changes, signal operation means it is going to increment the value of S. So whenever the S value changes here from 0 it becomes 1, the condition becomes false here. And that P1 enters into the critical section, executes, and see here, it is going to increment the value of S2. Now the chance is given to process P3. P1 gives the chance to process P3. As the semaphore value was also 0 here, even that P3 was stuck here. So whenever the value of P3 changes, now it is going to increment. Whenever the signal operation executes, it increments the value of semaphores. Now the S value becomes here 1, it enters into the critical section and it executes P3. So like this way we can change the order of execution using the more than one semaphore values. And whichever process we want to execute first, don't include the wait operation at all, directly it will get executed. And you can give the chance for other processes by using semaphore 1 and semaphore 2. For managing resources, next. Now suppose, this is for managing resources as I told you. Now suppose S is equal to 5. Then there are 5 processes in the critical section. S is equal to 5. S is equal to 5 means now suppose there are 5 printers. Okay, when there are 5 printers, in each printer one process can execute. So we can allow the 5 processes to enter into the critical section, not more than that. So whenever the process comes here to the wait operation, now the S value we have here 5. S value we have here 5. So wait operation means it is going to decrement the value of S. So it is going to decrement the value of S. It is going to make 4. Now that process, after decrementing the value of S, that process enters into the critical section and it executes. Now S value is 4. Now another process enters into the critical section. Now the S value was 4 here. Now when another process comes, now the S value becomes 3. So another process enters into the critical section. So when another process comes, the S value becomes 2. So like this way, all the processes enter until the S value is 0. So whenever the S value is 0, it will not allow the other process to enter. So like this way, the 5 processes can enter into the critical section and they can execute. Because there are 5 resources available. So in one resource, one process can execute. Then after coming out from the critical section, signal operation means they are going to increment the value. S value has become now 0. So whenever a process comes out, they are going to increment the value of semaphores. Now if one process comes out, it increments the value of semaphore 1. If second process comes out, it increments the value to 2. If third process comes, it increments the value to 3, 4 and 5. So like this way, in resource management, we can allow more than one process to enter into the critical section and execute if there are more number of resources available, not more than that. A semaphore will either allow or disallow access to the resource depending on how it is set up. So in today's session, we have studied what are the semaphores and how semaphores can be used to solve the critical section problem, that is mutual exclusion, progress, bounding, waiting, and also deadlock. These all problems can be solved in this using semaphores, and it is a solution for n processes. Thank you.